So remember that the exponential function is the inverse of a log function and vice versa. So once you understand what an exponential function's graph looks like, you can sketch the graph of its inverse function, in other words, the log function, by reflecting that exponential graph across the line y equals x. So the blue graph that you see is an exponential graph. The pink graph is the logarithmic graph. You can see how they differ when the base is bigger than 1 versus when the base is between 0 and 1. One thing I want you to pay attention to is that this key point 0, 1 now becomes the point 1, 0 on the log graph. Here it is again. 0, 1 becomes the point 1, 0 because when you when you look at the inverse function, you interchange the x and the y coordinates. Looking at the log graphs in each of these different examples, you notice a few things that are different now from the exponential properties. One idea is that the log function now has a vertical asymptote, which is the y-axis. So my vertical asymptote for the log function is the y-axis. All right, now that has the equation x equals 0. In this case over here on the right, once again, that vertical axis, the y-axis is your vertical asymptote for the log function. One thing you might notice as well is that the log function contains this x-intercept value, 1, 0, whereas it does not have a y-intercept. Okay, the domain for that log function now stays positive, whereas the range goes up and down forever. All right, so those are some of the properties you might notice on the log graph. We're going to put it together down here at the bottom. Domain of a log graph, like I said, all values have to be positive, stays to the right of the y-axis. The range is all real numbers. All right, the x-intercept now exists. It's 1, 0, whereas the y-intercept does not exist for a log graph. The vertical asymptote is the y-axis, also known as the line x equals 0. The function's increasing when a is bigger than 1, decreasing when a is between 0 and 1, smooth and continuous, and it contains the key points listed here. I like to pay attention to the x-intercept in particular. Find the domain of each of these functions. Now, this looks like a very difficult task. However, it is very simple once you remember something that I just mentioned regarding the domain of a log function. A general log function. So if you just have the log of whatever base of just x, the log of x has to be a number that is greater than 0 because remember that was the domain. X is greater than 0. Now in these cases for 42 and 46, it's a little bit different, but same concept. Whatever you're taking the log of has to be bigger than 0. The stuff around it does not matter. Whatever you're taking the log of has to be bigger than 0. In other words, the quantity 2x plus 3 has to stay greater than 0. So now we're going to figure out what values of x make that happen. Subtract the 3. 2x is greater than negative 3. Divide by 2. We find out that the appropriate domain for this example is all values of x that are greater than negative 3 halves. That's my domain. On 46, same concept. Whatever you're taking the log of has to be bigger than 0. Has to be bigger than 0, otherwise it won't exist. Okay, so that means I want to figure out where x divided by x minus 1 stays positive. Okay, x over x minus 1 stays positive. There's a couple things you have to consider. Where the top quantity is positive, the bottom quantity is positive, and then maybe each quantity is negative, and all different combinations of those scenarios. It's complicated. You know what? In the essence of what's going on right now, let's just go ahead and skip 46. If we were in class, I would work that out for you, but it's not important enough for you to know at this point. As long as you understand that the basic concept is that whatever you're taking the log of stays positive. That's the takeaway that I need you to have from that. All right, we're going to sketch the graphs that you see here. 3 to the x, so that means I'm crossing here on the y-axis and I'm going up. base is bigger than 1. I'm going to use that information to graph its inverse, which is directly to the right. Okay, the log base 3 of x is the inverse of 3 to the x, which means that now I have this point here, 1, 0. I also know that I have a vertical asymptote, which is the y-axis, and my graph goes something like that. All right, now use this log graph as your basic graph for the parts that come next. Use that basic graph. The ordered pair 1, 0 is crucial. The vertical asymptote is a line x equals 0. That's the y-axis. That's important for us to remember now when we graph our transformed graph in part A. This negative sign is a reflection, and this means reflect across the y-axis. So everything that's on the right goes to the left, and everything that would be on left goes to the right. So if I reflect the graph over here, my basic graph, if I reflect that now across the y-axis, what's it going to look like? Well, the point 1, 0 goes to the point negative 1, 0. Okay. The vertical asymptote didn't go anywhere. Everything else needs to be flipped as well. You're going to get this graph. I encourage you to check that on your, oh, you know what? We haven't discussed how to graph on calculators yet. Forget that I said that. Example B is another type of reflection. This time the negative is in front of the logarithm. That means reflect across the x-axis. So the point 1, 0 goes nowhere. Okay? The vertical asymptote goes nowhere. So what's going to change? Well, everything that was on the bottom from the graph directly above needs to go to the top. And everything that was on the top directly above goes to the bottom. So that's something that it might look like. Example C, we are going to do a horizontal, not horizontal, we're going to do a vertical shift down, vertical down by 1 unit. So the key point that I'm beginning with is at 1, 0, which is here. That's going to go down 1 unit, right? So that's going to move to here. Now moving down doesn't change the vertical asymptote. It stays exactly the same, and everything else stays the same. And so you're going to be going something like this. So I'm taking my basic graph that's highlighted here in yellow, take this graph, and I'm going to be moving it down 1 unit. Shape stays the same, just go down. Finally, example D, this negative 1 means a horizontal shift. We go to the right. Go to the right by 1 unit. So the initial point of 1, 0 goes to the right, becomes 2, 0. And this time the vertical asymptote moves as well. Instead of the line x equals 0, it's going to become the line x equals 1. So sketch that in there and keep the same shape otherwise. And it goes something like that. Solving log equations is going to be using the concept of going between the exponential form to the log form. So I'm referring to this first version as the exponential form and this other one as the log form. So when I refer to one or the other, you know what I'm trying to get to. Number 90 is in log form because of the presence of the word log. I'm going to change this now to exponential form. So the base 3 goes to the power 2. 3 squared is 9. Now you notice that I no longer have a variable that's part of a log. I do not have a variable that's in the exponent. It's very easy to solve. Using algebra that we already know about, you end up getting 11/3. Number 98, we will change this into exponential form. Treat the 5x plus 3 as one component. Okay, 5x plus 3 is just one quantity that stays together. All right, so base 6 goes to the exponent that I just talked about, staying all together, equals 36. Now I do have the variable in the exponent, so I need to try to use my exponential equation techniques I learned in the last section. I'm going to try to get the same base on both sides. Base 6 is going to work. I change 36 into 6 squared. Now that I've got the same basis, I can write the exponents equal to each other and solve for x. There you go. Next example, same process. Write this log form as an exponential form. So base 5 to the second power equals x squared plus x plus 4. Solve for x, get everything on the same side. X squared plus x plus 4 minus 25 equals 0. So x squared plus x minus 21 equals 0. And factor, what is that? Coming into a snag here. So if it does not factor, you are going to need to use a different method. And so the other option we have available to us is the quadratic formula. So we're going to have to solve this using the quadratic formula. Darn, I was hoping this would factor. Quadratic formula says we take solve. Whoops. Give me 1 second. Okay, solve using the quadratic formula. I couldn't find a way to factor because I could not find two numbers that multiply to give us negative 21 and add to give us positive 1. So that's how I knew it's not going to factor. So here we go. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. All right, I'm going to get some decimal approximations for these answers because I can't simplify any further, but I do want to know what my answers look like. (4.1) and the other answer negative 5.1. And so you have to decide if these are going to be okay to use. I don't think we are going to encounter any restrictions right now, so we are going to go with it and say that those are the two answers. We'll talk in the next section about how to know if those are appropriate answers. But for now, that takes us through the end of 4.4.